Hi, I'm Grace Lindsay. I'm an assistant professor of data science and psychology at New York University, and I'm going to be leading you through your tutorials today. And today we're going to be talking about using data science and machine learning to respond and adapt to climate change. So let's start by understanding what data science and machine learning are, what they do, and how they do it. So data science, you can see on the left, is a very interdisciplinary field. It pulls from concepts from mathematics, statistics, computer science, and its goals are to visualize, analyze, and find patterns in diverse data sets. So many of the techniques from data science are considered domain general in the sense that the same techniques can be applied to data from many different topics and be used to solve many different problems. Machine learning is also a somewhat domain general topic area that could be considered a subset of data science or of artificial intelligence. The main feature of machine learning is that it relies on learning algorithms. So these are algorithms that update parameters in a model based on data. So you're trying to build a model that can solve some kind of problem, relate different variables to each other, and those models have parameters. And in machine learning, you let the model be exposed to example data points and use those data points to update its own parameters. That's what makes it a learning algorithm. So in the machine learning, there are certain basic classifications of problems that you may want to solve. One basic type is regression, where you're trying to predict a numerical value. So for example, maybe we want to predict sea level rise in meters as a function of temperature increases. So because we're trying to predict sea level rise in meters, that's a numerical value. We want to know how many meters will it be. And we can do that as a function of temperature or other variables, but the fact that we're trying to predict that number, that's what makes it a simple regression problem. Now, alternatively, you can have a classification problem, and there you're trying to categorize data points as falling into different classes. So instead of trying to predict a value, you're trying to actually predict a category label. So this is a little bit different of a problem, but you could still be putting in something like temperature and trying to predict, say, which season that temperature recording was from. Okay, so here you want to apply the category label of winter versus summer as a function of temperature. And then a more broader class of problems can be called control problems. In these kinds of problems, you're trying to figure out what the best action to take is. So you can imagine something like a drone trying to respond to a wildfire, and it needs to plan a path where it can apply water to many different locations in a forest, and it needs to do that with the most efficient path and as quickly as possible. And so there it needs to take in information about the environment and choose the best action to take as a result. Now these problems, as you can imagine, can be very complicated. We're not going to deal with any control problems today, but just know that there are algorithms out there for working with control problems like that. So now let's talk about how this all relates to climate change adaptation. So machine learning and data science can be applied to many different aspects of climate change adaptation. Essentially anywhere where we want to automate the process of looking through data and making decisions, machine learning might be of help there. Situations where it would be helpful to better understand a system that we're dealing with and be able to predict things about it, we can also try to use machine learning there. So for example, predicting extreme weather events. As you saw, extreme weather events are going to become more frequent, they're going to become more severe, they're going to be more variable. And using all the data that we have about climate over the past several decades, we could try to build models that will help predict where extreme weather events will take and how severe they'll be in order to warn people about them and help them prepare for those extreme weather events. We could also think about tracking agriculture. So as climate change changes temperatures and weather patterns, it's going to change the growing regions and growing seasons of different crops. We can use things like remote sensing, which you've also encountered, in order to identify crops that are growing, predict crop yields, in order to help prepare people for potential food shortages or just planning where food will go. And then finally, things like responding to disasters, surveying wildfire locations, surveying the impact of hurricanes, that kind of thing. Being able to go through a lot of data, possibly from remote sensing, very quickly in order to figure out where resources need to go as fast as possible. This is another area where machine learning could help. Now, we do need to always, though, have caution in using things like machine learning and data science. They're not a silver bullet. They will always be limited by the amount of data and compute power that is available, and so that's something that needs to be considered. And it's always best to work with people who have domain expertise in the area that you're trying to apply machine learning to, because they will understand where things will go wrong, what the really difficult parts of a problem are, and why they're so challenging, and that can be very helpful for understanding the limitations of machine learning in a particular problem area. So let's talk about the learning objectives for today. Throughout today, you're going to learn the basics of linear and logistic regression, two very basic and useful machine learning models. You're also going to learn about Scikit-learn, which is the Python package that implements these kinds of models. You're going to explore two real-world data sets that are related to climate change adaptation. And you're going to learn about some more advanced models that could be applied to those data sets. And you're going to learn about a few different ideas like feature importance of a model and the problem of overfitting. So I hope you have fun learning about all these things because they are somewhat general techniques that once you get the basics of, you can really start applying to many different areas and kind of see how they work. So let's get started with the basics of linear and logistic regression. That's what you're going to be doing in the hands-on part of this tutorial. So linear regression is a way of solving regression problems. So we're going to walk through the format that the data takes and the math behind that model. So to start, the way that we kind of phrase a regression problem is that we're trying to predict a target value y using regressors x. So you're trying to connect inputs like x to a target value y. And in linear regression specifically, you're fitting a line to that data. You're assuming the relationship between x and y is linear, and that a simple line will be able to predict y from x. So what that looks like is this. If we recall the equation of a line from math class, you can see that we have our target value y, that's what we're trying to predict, and it is a simple function of x, a simple linear function of x. Now we do allow for some noise, which assumes that, things aren't perfect in the world, things are rarely related exactly by a line, there's also measurement error, so you can see these points here, for example, this represents our data, they don't fall exactly on a line, there's a little bit of noise. But there does seem to be some general linear relationship between x and y here. So for example, we could think of this as temperature in that previous example and y as sea level rise. That we're trying to relate those things. We're trying to predict sea level rise based on temperature x. So to do that, we have to provide the model with some data about the relationship between x and y. We have to provide it these example data points of pairs of x and y values. So that's what we provide to the model in order for it to learn. So what does the model have to learn? It has to learn this beta value, this beta coefficient value, which as we can see from this line here simply represents the slope of the line in this basic linear regression problem. So you can see some example slopes here, and basically the one in the middle probably fits the best, but the model needs to find what this beta value should be, what the slope should be. And not only that, you could imagine a problem where you have multiple regressors, multiple x's that you're putting in. So we could have temperature, but we might also have precipitation. We might have aspects about the coastline where we're trying to predict sea level rise. And so these would all be different regressors x, and the model would need to learn beta coefficients for each and every one of those, okay? So you can put in multiple regressors into this, and you're still trying to predict a single target value. So the way that the model does that is by reducing the residual sum of squares. That's represented here by this equation. And so what that is a measure of essentially how wrong the model is. So if the model that we trained had this slope was represented by this line, then we would calculate as a residual the difference between the model's prediction at a certain x value and the actual data point at that x value. So this difference between what the model predicts and what the data says, that's called a residual. And you do that for each and every data point, and you take the sum of each and then you square them all together, you take the square of each and then you sum them all together, and that is the residual sum of squares, and that is what the model is trying to minimize when it's finding these beta values. So it tries to find the beta values that make this number as low as possible, because you could imagine if there was no error at all, this value would be 0. And so you want the beta values that give you the lowest possible residual. And so if the model is successful, it will find the beta values that give you a very low sum of squares. And then when we think about how we evaluate how good the model is doing, we're actually going to use a somewhat similar metric for evaluating how good the model is. And so this metric is called the coefficient of determination, or R squared, it's also called. And it is a measure of how much of the variations in the data the model can capture. So it relies on this residual sum of squares in the equation for R squared here, but just that value alone isn't contextualized enough to give you a good measure of performance. So what you have to do is divide that value by the total sum of squares. And so that is a metric that is just about the data itself. It's not about the model. It's just asking how much variability is there in the data. And so that's a function of how much each data point, each x value, how much it differs from the mean x value. That's how you calculate this bottom term here. And then you want this r-squared value. The best possible r-squared value is 1. And what that means is that essentially the residuals are 0, so this term cancels out. You just get 1, and that means you know you're doing very well. If this isn't exactly 0, but it's a small number compared to how variable the data is in total, then you still have a good r-squared value in the end. So that's how you interpret the r-squared value. Okay, so that's linear regression. That's what we're trying to do with linear regression and how we evaluate linear regression. Now let's talk about logistic regression and the relationship it has to linear regression, but also how it can be used to solve classification problems. So logistic regression can be used to perform binary classification. So as you recall, before I gave the example of predicting what season we're in as a function of different temperature or climate variables. So that's an example of binary regression because we have two different classes, summer or winter in that case, and we want to put each data point into one of those two classes. So the equation at the heart of logistic regression is very similar to the equation of linear regression. So as we recall, this is the equation of linear regression. We're predicting this target value y as a sum of the x terms with each their different beta coefficient. Logistic regression, the equation looks like this. So you can see the same sum of the weighted x values in here, but that's not where logistic regression stops. After you do that sum, you pass it through what's called a link function. And in the case of logistic regression, that link function is a sigmoidal function, represented here by s. These are called sigmoidal functions because they have the shape of an s. And so what that function does is it takes this sum, and this sum could be any number, right? It can be negative 50, it could be positive 3,000. It's just whatever the sum is. But the sigmoidal function swishes all of that into being between 0 and 1, as you can see here. So by passing this through the sigmoidal function, you get values that are only between 0 and 1, okay? And we call the output of that p here. Now, that's not quite enough. That's still not a category, right? Now we just have a number between 0 and 1, but we don't have a category label. So how do we turn that into a category label? Well, let's say that we're, again, trying to predict or trying to label which season we're in, and we know temperature as x1 and humidity as x2. Those are the variables we're going to use. And so we have a data point where we pass those variables into our model. We get the sum, and then we pass it through the sigmoidal function, and we get this output p. And in this case, the p is around 0.8. So what we do here to turn that into a category label is simply apply a threshold. So any value above 0.5 is going to be category 1, which is summer, and any value below 0.5, so let's say for this data point, we pass it through this function that's below 0.5, that's going to be category 0, which is winter. And so that's how we end up being able to apply binary classification labels to each of these data points. We simply binarize or threshold these p-values into 0 or 1 labels. Okay, so let's say we did that, we ran our model, we got its predictions for all the different categories, and we want to know how well the model is performing. We also want to be able to train the model to perform well. So here is the term that we use to train the model to find the right beta coefficients. And so the model wants to minimize this log loss term. It wants to get as low as possible on this log loss term, and that means that it's found good beta coefficients. And so the way to understand how this log loss function works is that each term represents how well the model is doing for a different class. So this first term tells us how well the model is doing on category number 1, which in our case is summer. So the way to understand this is if we think of the L values here as the correct label, so where the data actually was taken from, was it a day in summer or winter, then the L term here would be 1 if it was summer, and it would be 1 if it were summer here, but then we do 1 minus 1, that's 0, and this term drops out. So we're left just with this term when we're looking at a data point from summer. And then we're evaluating how well the model is doing on that summer data point by looking at the log of the p-value. So if the data the model, were very certain that, this is a data point from summer and the p-value here was 1, then the log of 1 is 0. And so this log loss would be low because it would be 0 if it were performing perfectly well. If this model were outputting a p of something closer to 0, a low number here, this log value would be a negative number, which multiplied by -1 here would give you a large number. The log loss would be high, and that would be bad. So this is forcing the model to try to provide a p-value for a summer data point that is as close to 1 as possible. And then the same thing happens over here. If the true label is 0, if it's winter, then this first term drops out. We just have 1 minus 0 here, and this term remains. And the same thing is kind of happening in reverse, where this p-value is encouraged to be as close to 0 as possible in order to minimize this log loss function. So that's how you tell the model what you want it to do, how you tell it to give each data point the correct label. And through that, it finds the beta coefficients that can do that. Okay, but then evaluating this model once it's trained and once we want to understand how good it is at classification in particular, one metric is accuracy. And so accuracy is just the fraction of correctly classified data points out of the total data points that you tested the model on. Now, accuracy can be a little bit misleading, especially if you have unbalanced data points. So what that means is if you have a data set where, let's say, 90% of the days that you recorded temperature from are in the summer. And so the model could simply learn to label everything as summer, and it would be getting 90% accuracy. And so you might look at the accuracy and say, oh, 90%, that must be good, but it's because of the imbalance in the data set. It's really just not learning anything. It's just saying everything is summer. And so you want to think about other ways of looking at the model's performance that can help you see those kinds of effects. And so one way to do that is by plotting a confusion matrix. So this is a plot that shows the true category, so the actual label from the data and the label predicted by the model. And if your model is performing well, you should have high values on the diagonal here and low values on the off diagonal. That means that the model is predicting the true category most of the time. But if your model isn't performing well, this would help you see the ways in which it's failing. So either it's predicting things as winter when they're actually summer, or it's predicting things as summer when they're actually winter. But either way, you'd be able to see in this confusion matrix the way in which the model is failing if it's producing a lot of errors. Okay, so one thing to keep in mind whenever you're trying to evaluate a model from machine learning is that you have to think about the data that you're testing on and how it relates to the data that you trained your model on. So we can give the model these data sets and it learns to get the beta coefficients for those data sets, but that's not representative. How well it performs on those data sets that it learned from is not representative of how well it will perform generally if you showed it new data. So you always want to have what's known as a test set. And this is data that you don't give to the model during training. It's not used in the learning algorithm to update the beta coefficients. It's data that's completely held out separately. And then you evaluate your model on that test data. And that way you know that the model is learning something that will generalize to test data. So it's definitely something to keep in mind, and you're going to see throughout the coding exercises today that we always have a separate test set. Okay, speaking of the coding exercises, what you're going to use is a package called Scikit-learn, and that has all of the basic built-in functions for working with these kinds of machine learning models. So Scikit-learn is super commonly used in academia and industry. It's a really great toolbox to learn the basics of because you'll be able to apply it in many different settings, and it has many, many different models built into it. It's just really a great interface where once you learn the basics, you can kind of do almost anything that Scikit-learn has to offer. And it interfaces nicely with other basic Python packages like NumPy and pandas. So one thing to know about this, as you'll see, is that these models, or they're also called estimators in Scikit-learn, are Python objects. So you're going to define the model and you're going to provide the data for it to train on or fit to. And then it has also built-in ways of evaluating the model's performance. And so depending on which sort of model you're building, the way that the model is evaluated will be different. As we talked about in linear regression, we're looking at something like R squared. In a classification problem with logistic regression, we're looking at accuracy. So just know that the score method in Scikit-learn, depending on what model you're using, it actually returns a different value because it's using the metric that's most appropriate for the model that you trained. But yeah, so the interface here is super standardized. You're going to see just how easy it is to use different models using the same basic way of writing the code and the same ways of evaluating it. Okay, so I hope you enjoy exploring Scikit-learn and testing out logistic and linear regression with some synthetic data.